Hello everyone and welcome to this video. Today we're gonna discuss multiple integrals. We're gonna talk about some of their properties and how they can be used to obtain the volume, area, and the average value of a function. Now we will start with double and iterated integrals over rectangles. So first let's start with the definition of a double integral. Now, and let's start to define the environment for defining this double integral. Now we can see this is a rectangular grid and we partition this region R, we call this region R, into small rectangles of area delta A K. Now what does delta AK mean? It basically means multiplying delta xk by delta yk. So multiplying the change in y, this is the change in y, delta yk, and k is basically refers to the square itself. So this can be k equals 1, this can be k equals 2, this k equals 3, so referring to each square, just like a reference. So now k is any square, so say k here is the square in the middle, okay? And so the area is basically multiplying the change in y by the change in x for the square k. It's all about changing. Okay, and we then, if you want to do, for example, this square, we're gonna basically do the same. So if we say this square has a value of k equals, let's say 25. I'm not sure what is the real value of k. We need to count all of the squares and then assign a value of k to each square, but I'm assuming that the value for k for the square is 25. So the area here is just delta A of 25 equal the change in y of square 25, here the change of x in square 25, so equal delta y 25 times delta x 25, and this will give us the area for square 25. Now we need to find the values, the exact change of value, and this can be obtained by having the function, for example the function f of y and the function f of x, and then we do the Riemann sum of all of these squares to get the approximate area of the whole function. So this is exactly the notion that we use, similar to an integral in a regular integral that we used to do in calculus 1. So yeah, so this is basically the definition of our rectangles. Now if we move on to 3D, now we moved on from 2D to 3D. So if you want to approximate a solid, okay, so now we are talking about 3D, so we're talking about solid. In the previous, in the regular integrals, we were talking about a region. So now this is a region, and we were dividing that region into squares, into rectangles. We're dividing it into approximating rectangles and taking the limit of these rectangles as n approaches infinity. So then as the number of these rectangles increases, the approximations become better. So we're taking rectangles. Now if we talk about a solid, which is basically what we have here, let's try to draw a simple solid. Now if we're talking about a solid, so let's say a cube like this, let's say this cube. Now we want to approximate the volume of this cube. We used to approximate the area, now we want to approximate the volume of this cube. How can we approach it, do you think? Okay, I know the cube is a to the 3. The volume of the cube is the length of one of its side multiplied by 3. Okay, that's easy to understand. That's something we know. But what if you have something like this? Now, how would you find the volume of this? Now, this gets more complicated because we don't have a formula for these solids and shapes. We don't have a formula for them. We only maybe know the function of the curve that's above them. So maybe we have a function and then we want to find the area under that function, which represents basically the solid. So now what we can do is we can use an approximation, which we can basically show you here in the cube. Now if you want to approximate here, we can use boxes. We can approximate this using boxes. What do I mean? Let me show you. Now this, see, I'm approximating by drawing some boxes, and I can continue all the way filling the cube. And now what I can do is, if I want to improve the accuracy, the approximation of this box, now I can just find the area, the volume of each of these boxes. The volume of each of this box is basically the area that we got here, delta AK, the one that we got here. So imagine now this is the upper face of the cube. This graph, this whole graph is the upper face of the cube, and now we have delta AK, and the volume is basically the height, okay, h times delta AK. Now in our example here, the height could be constant. The cube has a constant height, which is, we can say 10 for example, or 24, anything. So any height would work here. However, here in the solid, we don't know the height at each point, but we have a function that represents the height. So we cannot identify the height exactly, but we have a function that is changing. The height is changing with respect to x, with respect to y, it's always changing. So now the height, since it's changing and we have a function that represents the height, then we can basically say that the volume of one box, Vk, is equal to now this. I want to see this. Now this is basically the volume for one cube, for one box of the boxes of the approximating boxes. Now if we find a volume for k, for box k, and then we find the volume for box k plus 1, and find the volume of the first box, second box, and k's, as we said, represent the number of the box. So we have many boxes and then we want to identify them by a number. So k is that number. It can be any number, it's just an arbitrary number. So let's say here, k can be 25 or 50 for example. Now this is only one box. This, what I wrote here, the k is one box. Now if I want to find all of the boxes, the sum of all of the boxes, I can do the Riemann sum. What is the Riemann sum? Riemann sum is just summing from n equals to 0 to some value k, to some value k. And now let's say k and then here n. Okay, this represents the number of boxes and this represents the box itself. The k represents the index of the box. Now if you want to sum the volumes vk, it's gonna give us the Riemann sum from k equals 0 to n of f of xy times delta a k. Now this is an approximation of our volume. Now we are approximating our volume by summing all of the boxes. Now so for let's take this solid that we skipped for a bit. Now this solid, if we wanted to approximate the box at point k, okay, so first you would need the function, the value of the function, the height, let's say the height of the box at point k, point x equal xk and yk. At that point we need to find the height at that point, and then we need also to find the area of the box at that point, which is delta ak. So we would need delta xk and delta yk and multiply those to get the area delta ak. Remember, delta ak is delta yk delta xk. Okay, and now we can do this also for other boxes. So if we draw a different box here near this, like this, go down, and now this is a different box, say like this. So this is a different box and it will have a different value for f, and so it will have a different volume. And we also can draw a box here. The value can draw a box. Now these boxes just approximate, they are not the real value of the volume. If we draw all of the boxes here in the region and add them, it will give us a good approximation, which is represented by the Riemann sum here. It will give us a decent approximation of the volume, but it will not be the exact volume. Now if you want to get the exact volume, what do we need to do? We need to take the limit. So our sum that we just gathered, okay, k equals 0 up to n of f of x, y, dA. If we take the limit of that, we take the limit as Sn of Sn as n approaches infinity. What does n approaches infinity mean? Well, as the number of boxes. So what did n represent for us? N represented the number of boxes. And now if we say that the number of boxes increased up to infinity, so we had infinitely many boxes representing our volume, then we're gonna have the limit as n approaches infinity of the Riemann sum from k equals 0 up to infinity f of xy dA. And this is, my friend, basically the definition. We have just wrote the definition of an integral, which is the limit as n approaches infinity of the Riemann sum of function, which is basically was defined as the double integral of f of x, y. Now, of course, it's not dA, this is delta a k. Okay, so we did not reach the dA. Delta a, dA is used for integrals only. Okay, so it's delta ak now. And then it becomes dA over the region R. And that's exactly the definition of a double integral. And of course we take delta k as it approaches 0. And as we make n approach infinity, delta AK, the area of each rectangle approaches 0, which is something that we want, since we want the rectangles to be, the boxes, sorry, I'm talking about the boxes here, we are talking about volume. We want the boxes to be as small as possible to represent our Riemann sum and to represent our volume. And so this is basically the definition of a double integral. Now, how can we apply this to volumes? Let's see how can we do this. Now, this is what I'm talking about. This is a rule basically. As you can see, for n equals 16, so we have 16 boxes. If you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here we have exactly 16 boxes, and as we said, n represents the number of boxes that we're going to use to approximate. Now, if we increase the number of boxes up to 64, we're going to have more boxes and we're going to have a better approximation of the volume. And now if you go even higher, n equals to 256, then we're going to get an even better approximation. And what do you think will happen if we go all the way to n equals to infinity? We have almost infinitely many boxes. What do you think will happen? Yeah, it will just be the volume. It will be the volume itself, the volume of the solid that we're trying to find. If you notice, as the number of boxes increases, the area of each individual box decreases. As you can see, the area of the individual boxes decreases. So for n equals 16, it was bigger, then it becomes smaller, and then even smaller. And that's exactly what we have here. That's exactly what we have here. As n approaches infinity, the area of each individual box approaches 0, a decrease. And so that's what we are doing here basically. So as n increases, the Riemann sum approaches the total volume of the solid. And so now this is another solid, okay? And this is also a way to obtain the cross-sectional area. So in order to obtain a cross-sectional area of at a specific point of the solid, we can basically hold, for example, this is our plane representing a solid, representing a cross-section. So this plane represents a cross-section of the solid, and we want to find the area of this cross-section. Now, in order to find this area, we can do the following. A of x equals the integral. We want to find the cross-sectional area from y equals 0 to y equals 1. And then we plug in the function. So this is only a one variable integral, okay? Then we go dy. Now what did we do here? We are holding x constant, and then we are integrating with respect to y. So let's do this integration. Now this will give us 4y minus xy minus y squared over 2 from 0 to 1, which is a of xy equals 4 minus x minus 1 over 2. A of x equals 16 over 4 minus 1 over 2, 8 over 2 minus 1 over 2 is just 7 over 2 minus x. Now this is a function for the cross-sectional area. If we want to find this cross-sectional area at any point x, then we can just substitute that point x. So for example, let's say here x is equals 1.5. If we want to find the area the cross-sectional area of the solid at the point 1.5, we're gonna have 7 over 2 minus 1.5, and this is the cross-sectional area there. Now if you want another value, for example 1, you can get 7 over 2 minus 1, and etc. Now someone would ask, what if we want the cross-sectional area with respect to x? So we don't want the cross-sectional area in the direction of the YZ plane. We want the cross-sectional area, for example, the direction of the XZ plane. So we want this cross-sectional area. So what should we do? I would like to draw it better. So okay, so someone would want the cross-sectional area of this region. I want it in the other direction. How would I do that? Well, that's easy. Basically, I can do a of x. No, now we are doing with respect to y. So fy is the integral. Now we have it here from x equals 0 to 2. Okay, as you can see, this is 2, and from 0 it goes up to 2. And then we can integrate with respect to x and hold y constant, exactly as we did, but we're gonna change the variables. So minus x minus y dx. Now we hold everything constant. Ay was the integral from 0 to 2. Okay, and then 4x minus x squared over 2 minus xy from 0 to 2. Now this will give me a of y equals to 8. Now we're substituting here x equals 2, x equals 1, just to not mess up between x and y. And then here is 4 over 2, which is 2, minus 2x. So a of y equals 6 minus 2x, sorry, 2y. Okay, I was just talking about not messing up. And okay, so 6 minus 2y. So now, if we want to find, now this is a function of the cross-sectional area with respect to y. Now if we want to find the cross-sectional area at, let's say, y equals 0.5, it's gonna be 6 minus 2 times 0.5. If we want at y equals 1 over 3, then we have 6 minus 2 minus 2 over 3. And that's exactly how we find the cross-sectional area of a volume. So this is the way to do it. We can just, it's a regular integral with one variable. That's easy. That's exactly what we did. So to obtain the cross-sectional area, we hold y fixed and integrate with respect to x, and that's what we did. Hold y fixed and integrated with respect to x. Okay, so now we're gonna go back to double integrals. I'm gonna talk about Frobenius theorem, which is the first form. And it states that if f of x, a function of two variables, is continuous throughout the rectangular region R, a rectangular region, and R basically poses the conditions that x should be bigger than a and x smaller than b, and y is bigger than c and y smaller than d, then it's basically, if we draw it in a 2D region, 2D coordinates, x, y, then we're gonna have something like this, where this is A, this is B, this is C, and this is D, and basically this is our region R. This is our region. So if a function is continuous throughout the rectangular region, then we have the double integral of f of x dA over the region R will basically equal to this double integral. And what is this double integral? Well, let's just break it down. So dA, as you can see, let's first look at the dA here. As you can notice, this dA became dx dy. So, and it makes sense since, you know, dA is originally dA is originally delta AK, as we discussed. Okay, and you know what delta AK? This is delta AK. It's a rectangle beside other rectangles. Okay. Now this is delta AK. And delta AK is basically the change in x multiplied by the change in y. The change of x multiplied by the change of y. So, and dx is just originally delta xk, and dy is originally delta yk. So it makes sense to write that since delta ak equals delta xk times delta yk, so it makes sense to write dA equals dx times dy. And that's exactly what's happening here. And also, we need to empathize a point that the order matters, since we are talking about integrals. However, like in finding dA, it does not matter, but here in integrals it matters, and I will tell you now why this matters. So now we discussed the dx dy. Now let's discuss the part where we have the limits here, a, b, and c, d. So this is basically the same as you would do it for a regular integral. Okay, and you would make sure you match up the limits. So for dx, the limits are going to be from a to b, since in the x-axis we have the limits a, b. And for dy, which is the outer integral, the limits are going to be from c to d. So the limits are going to be from c to d, alright? And they're going to match the differential dy. Now there is also another form which is the opposite of that form, which is dy dx, and basically it's the same. Dx dy is the same as dy dx, but you need to make sure you match your limits of integrals. So if dx is inside, then you're gonna add the limits for dx in the inner integral, but if dy is inside, then you're gonna add the limits of dy of y in the inner integral. So this matters. The order, the limits, and where they are placed matter, but depending on the differentials. Now this way, you're gonna add first in the other inner integral the limits of integration, and the outer integral is gonna be the outer limits of integration. So it's gonna be AB, which are with respect to x. And that's simply how it is. That's the theorem. Now if we want to apply it, we can go through an example. So example 1. So we're gonna calculate the volume for a function. When he says calculate this, it means the volume. Okay, a double integral is usually a volume, but there are cases where it's not, and I will tell you when. But if it has a function, that means it's a volume. Function dA is a volume. And then we have this region, rectangular region. We can try to solve this ourselves. take a screenshot, and let's do this and copy it to my board. Let's go to freeform. Okay, so this is our example. Let's try to solve it. Now he wants the double integral, or let's say find the volume. Okay, find the volume of this, of the region under this curve bounded by this region. So let's do it. Now we're gonna have the double integral of r f of x y dA is gonna equal, we're gonna use the theorem. Okay, Fibonacci theorem. So we're gonna first 100 minus 6x squared y. Now we're gonna decide, do we first do dx dy or we do dy dx, and it's completely up to you. We can decide either to have either of these, and it's up to you, but you're gonna make sure when you have one, you have chosen one, you need to stick with that integral in terms of the limits of integration. So let's say I would do dx dy. Okay, so now I did dx dy. So in the inner integral, I'll need to add the limits for x, so it's from 0 to 2. For the outer integral, which involves dy, we're gonna add the limits for y, which are negative 1, 1. And now we integrate. Now how do we integrate this? Well, basically we're gonna integrate as we do with regular integrals, but we're gonna do it one at a time. So first we're gonna take the inner part, this part, the inner integral, and evaluate it as a regular integral, of course taking any other variable than x as constant. Okay, so it's not called a partial integral. I'm not sure, I don't think it's called a partial integral, but basically that's what we are doing. It's the same as we did with partial derivatives. We took everything constant except the variable that we will differentiate with, and here we'll do the same, so but with integration. So we'll integrate this. Let's do, yeah. So if we take it separately to 100 minus 6x squared y with respect to x is gonna give us what? It's gonna give us 100x minus 2x to the 3 y from 0 to 2. Now evaluate this. Of course we're gonna say x equals 0, 2. Okay, so we don't mess it up with y. Y is treated as a constant. So 200 minus 2 to the 3 is 8, so minus 16y. Of course, minus 0. We don't need that. Okay, so now this is the value that we got. Now we go back to our integral here. Okay, and substitute. So substitute the value for the integral we got. So from negative 1 to 1, so 200 minus 16y dy, just a regular integral with one variable. It's very, very super simple. So 200y minus 16 over 2 is 8y squared, from negative 1 to 1, just basically 200 minus 8 minus 200 minus 8. So these cancel, and then we have the value to be 400. So the volume is 400. Let's check our answer. As you can see, 400. Now he solved it also with respect with in the other way around. So he did dy dx. Yeah. So he did dy dx, integrated it, and then did exactly what we did, and then he got the same answer. If you do this, and this is true for any function, for any region, if we do it with respect to y first, then with respect to dx, it's gonna give us the same answer as if you do it with respect to dx, then dy. So it's not an issue or something detrimental. Now, as you can see, it's a double integral. It gives the volume under the surface over the rectangular region. Now someone would ask, yeah, see, this also a different function which gives us, the volume under the region. Now, what if the surface, not the surface, what if the region, someone would ask, what if the region is not rectangular? What if we did not have a rectangular region? Maybe we had a circular region. We had, or let's say, a non-uniform region, something like this, or something like this. This is our region. What can we do about this? How can we integrate? Now I'll tell you what we can do. And now this is our second part, double integrals over general regions. And so this is our regular double integral definition. Now this is our irregular region, which is omega, and this is R. Now this is a good example of what I'm saying. Or this is a good example. So as you can see here, the region is circular, and this is a volume of a shape. It reminds me of sweets during our holidays. We have a sweet that looks this shape. So now this region is circular, and we do not know how to, we know only how to find the volume over a rectangular region. Now how can we do this? How can we evaluate the limit over this region? Now basically it's all the same concepts. As you can see, we have delta AK, which is the area of the box of the rectangle here, and then multiplied by the height f of x. This is give us the volume of the box, and then we have the function z f of xy. This is our surface, which is the one that we want to find the volume under, and the volume is basically the limit of f of xy delta ak, which is the indefinite integral of fxy dA. Now we define the volumes of solids with curved bases as the limit of approximating rectangles. So it's basically the same way that we'll do it. We'll have other rectangles approximating this region. Now we understand how to do it with the Riemann sum. I think we understand how to do it with the Riemann sum. We just have these little rectangles and we add them. But what about an integration? How can we do it with this double integral? Is it possible? Well, yeah, that's exactly what we are going to do. So imagine now we have, imagine we have a region like this. The region is this, and then this is the region. And imagine that this is a function, g1 of x. This is a different function, g2 of x. And these are just some values, a, b. So now we have this region and we want to find the volume of the surface under, the volume under a surface over this region. So what would someone do here in this situation? Well, what we can do is the following. We can treat the functions g1 and g2, we can treat them as limits of integration. Now what do I mean by that? Well, it's exactly like it sounds. Limits of integration. And so now if we want to differentiate now if we want to differentiate with respect to y, what we can do, since y extends from g1 of x up to g2 of x, we can just put in these functions as the limits, okay? And I hope you can visualize this. And then for the x's, we just say that if we're integrating over x, we say that we're gonna integrate from a to b. And this is a, you can see it, this is the line b, and this is the line a, and this is the function g2 of x, and this is the function g1 of x, and this is the region R. And we are integrating over this region, finding the volume under this surface. Okay, and how do we do that basically? So it's very simple. So first we do is we find the integral, or we find the area under a curve as we did in 2D. So let's erase this. Now let's visualize this. Let's zoom in more. I want to show you this. Now first, as you can see here, we have an area. This is a of x, which is what we found before. We found a of x by integrating f of xy with respect to x, and this is exactly it. We are finding this a of x, so we are integrating over this surface, over this curve, the curve above, and we are doing a regular integral with rectangles, approximating rectangles. So these are approximating rectangles, and by that we are doing the integral. And when we find the integral, we find the cross-sectional area of this. Now what if we add the cross-sectional areas from the line A up to the line B? What if we add them? So we evaluate the cross-sectional area at each point here. So we have here a cross-sectional area, have also here another cross-sectional area, and we have then this cross-sectional area, so that's a different one, and then here. So these are all cross-sectional areas. We add them. What if we add them all? What's gonna happen? Well, basically it's exactly as you've guessed, we're gonna get the volume. And that's basically what we are doing here by evaluating the limits g1 and g2. We are here first getting a function for the cross-sectional area. That's the first thing we are doing. And then we are adding all of the cross-sectional areas to get the volume. And that's basically how we do it for non-regular shaped regions. I hope you understood this part. Now we're gonna want the second part for some reason. Let's just do this. Okay, now we can go over some examples. Okay, so this is also the same thing. We have two regions, h2 of x, h2 of y. Now this is with respect to y, h1 of y, and then we're just gonna reverse the order here. So first we have dy dx, now we have dx dy. And then we're gonna plug in h2 and h1 as boundaries, and then this is the stronger form of Fibonacci theorem. So let f of x, y be continuous in region R, then 1. If R is defined by x bigger than 1, a, and smaller than b, and y bigger than g1 of x, smaller than g2 of e, then with g1 and g2 continuous on ab, we get this. And the same goes for the other case if R is defined by the region y bigger than c or smaller than d, and x bigger than or equal h1 of y, smaller than or equal h2 of y, with h1, h2 continuous on CD, then we get the other form. Now this is an example. Find the volume of a prism. Okay, so find the volume of the prism whose base is the triangle in the xy plane, bounded by the x-axis and the lines y equals x and x1. So let's try to draw this region first. So I already had it drawn, but let's draw it again. Now this is the x-axis, this is the y-axis, okay, and then we have the line y equals x, which is just this line. Basically this line, y equals x, and then we have also the x-axis. So we have the x-axis, and we have the line x equals 1. So let's say this is 1, and then the line x equals 1 is just this line, and the region is the region bounded by the x-axis, the lines, as you can see here. This is our region. So it is a prism. The volume is a prism, and this is our region. Now let's try to solve this ourselves. And then we check our answer through the solution manual. Going here. Now getting this and that. And this is our question. Now let's find the volume. How would we approach this? First again, let's draw our region. The region goes from y equals x, and then this is 1, so it goes here, x equals 1, and the x-axis of course is bounding these, so we have this region, which is the region R. And now, since this is basically a region bounded by two functions, y equals x and x equals 1, we can do something like we did before. So we can use a double integral of f of x, y, and then we start with dx dy like this. So we have dx dy, and now we want to decide which way do we want our rectangle to be. Do you want them to be horizontal rectangles, or do you want them to be vertical rectangles? We can do both, but let's start with horizontal rectangles. Now for horizontal rectangles, we'll need to first have integrate with respect to y, and for that we need to change. So for horizontal rectangles we're gonna integrate with respect to y, and if you're wondering why, so basically this is dy, so you need to integrate with respect to y, and this is the height. So now let's try to do it with our function 3 minus x minus y dy dx. Now we need to decide on the limits of integration. Now the outer limit for x is very simple. It's basically from x equals 0 to 1. Now this is simple. Now what about the integration for y? Now we need to decide what is the lower function. The lower function here is y equals x, or x equals y, but here we need to write x equals y. Okay, or actually it's y equal x. Okay, and the lower function is just I need to make sure, is this correct? Now here we also have 1, so the intersection is 1 basically. And we're gonna start from 0, y equals 0. And yes, that's exactly how it should be. I hope so. Yep, exactly how it should be. Okay, so let's solve this. Now we get the integral from 0 to 1. We're gonna have 3y minus xy minus y squared over 2 from 0 to x dx. Now this is gonna be 0, 1. Of course, this is y equals x and y equals 0 dx. So 3x minus x squared minus x squared over 2. And if we plug 0, we're gonna get 0, so just we get this function dx, which is gonna equal to integral from 0 to 1 of, so minus 1 over 2 minus 3 over 2, 3x minus 3 over 2 x squared dx. And we're gonna get 3 over 2 x squared minus 1 over 2 x to the 3 from x equals 0, x equals 1, which is 3 over 2 minus 1 over 2, which is 2 over 2 or 1. And that's our answer, that's our volume, exactly as we get it here. And also there is our other way of finding this volume. Basically you can find this volume by doing integrating figures first with respect to x and then with respect to y, or basically doing the vertical boxes method. Now we did this method, okay, but if we want to do vertical boxes, so we need to integrate with respect to x first and then with respect to y, and it will, at the end it will yield the same answer. And for the limits of integration, if we want to determine the limits of the integration, let's just set up the integral for for vertical rectangles. So if we want to do, no, let's say, let's just set up the integral and not evaluate it. 3 minus x minus y dx dy. So for dx, what are the limits gonna be? So the limits are gonna be basically x equals y. So this is the upper limit, okay? Or is it gonna be the lower limit? So it is the lower limit. It is the lower limit. So x equal y is gonna be the lower limit since it's the region up, and the region that's lower or down. So this region, which is x equals to 0, it's gonna be the upper part. Okay, and then for the y, basically we get from 0 to 1. Can evaluate it from 0 to 1, and this will give us basically the same answer as our first integral. It's gonna give us 1, and this is exactly what we got. As you can see, it's exactly the same integral. If you evaluate it, you're gonna get the same value. Now this is a visualization of what he did, and this is exactly what we did. These are our rectangles, horizontal and vertical. As you can see, this is a prism with a rectangular base in the XY plane. It's very interesting to see such a thing. Now this is the region of intersection, and yeah, so you can visualize the prism, and down here is our region, as you can see. And so we also have the region of intersection. And we can find the limit of integration by first integrating to y with respect to y, then with respect to x. So these are just some different examples. So here, for example, the line leaves at x equals the square root of 1 minus y squared, and here it enters at x equals 1 minus y. So the limits of integration are gonna be just x equals square root of 1 minus y squared, of course, and then like this. So okay, so we're gonna have here square root of 1 minus y squared, and here we're gonna have 1 minus y, and then the function of xy, dy, and then dx, and dx is basically from 0 to 1. It's also a different region. We have many different examples you can try. And here, okay, so here are some properties of of double integrals. Okay, if we have two functions, f of xy, g of xy, which are continuous in the bounded region R, then the following properties should hold true. First, we have constant multiple, and it's basically the same for regular integrals. If we multiply a function by c, then we can take that constant c, which c is any number, and take it out of the integral and evaluate the integral separately. And that's the constant multiple property. Now we have sum and difference property, which basically states that if we have a function f of x and another function g of y, if we add them or subtract them, then we can separate those two functions into two separate integrals. F of xy, the double integral of f of xy dA, and over the region R, and the double integral of g of xy dA, and then there is a plus minus sign here. And also we have the domination property, which states that if a function, we say that the double integral of a function dA is bigger than or equals 0 if the function itself is bigger than or equals 0 on a region R. So this is just basically stating that if a function is bigger than 0 on region R, then the double integral is gonna be also bigger than 0 and positive. And I think it holds true for negative functions. If it's less than 0, then the double integral is gonna be less than 0. And also if you have here, this is another property, part B. If a function, the double integral of a function, okay, of a multivariable function over dA is bigger than another double integral of another multivariable function if the first multivariable function is bigger than the second multivariable function on the region R. And then we have the property of additivity, which says that the double integral of f of xy, a multivariable function, should equal over a region R is equal to the double integral of that function over region R plus the double integral of that function over region 2, given that R is the union of two non-overlapping regions R1 and R2, which basically means R is equivalent to R1 union R2, given that and R1 do not intersect R2. So these are the conditions. Okay, so for this to apply, let's rewrite it. R is the union between R1 and R2, and R1 does not intersect R2. Okay, which can be illustrated here in this photo. So we have here R is the union, so it's basically R1 plus R2. The region R is R1 plus and R2, but the thing is that R1 should not intersect R2, so there should not be any overlap between the two regions. If there's overlap, then this is an issue. But if there's no overlap, then this property holds true, which is the sum of the integral over the separate regions is equal to the indefinite integral over the whole region. And this is the additivity property for rectangular regions. Okay, so this is also an example which we can solve. So here are some examples. I'm gonna skip those, and I'm gonna go to the lecture itself, which is the area by double integration. Now, this is where I told you that the double integral is not necessarily, remember I told you that a double integral usually represents a volume, but not necessarily a volume, not always. We can also use the double integral to find the area of a specific region. And that's, you know, a very useful thing to have, since it's gonna make it easier for us. It's gonna make it easier than even a single integral. So basically the formula is A equals the double integral of the differential dA over the region R. Okay, and let's see some examples. So one example, find the area of the region R bounded by y equals x and y equals x squared in the first quadrant. Okay, so we can sketch the region. Do you have a sketch of the region? Yes, we do have a sketch of the region. This is the region. And basically we're gonna plug in the boundaries. So these functions as the limits here. Let's try to solve it real quick, and this is our last example for today. We're gonna call it quits. Okay, so if you can go here and solve this. Okay, so he wants us to find the area of the region. Now let's draw the region. So it is, the region is in the first quadrant, so XY. Now we're gonna draw this. Y equals X, and then Y equals X squared, like this. Okay, and so the region is just here. So this is 1, this is 1, and now we want to find the area of that region. So the area is just the double integral of the differential dA. Now what are our boundaries? So we just can, instead of writing dA, we can write dx dy. So first for x, what are the boundaries for x? If we want to do it for x, then we're gonna use the vertical rectangles, and the vertical rectangles basically we're gonna be doing y equals x, y equals x squared, then we're gonna do for y from 0 to 1. Let's check our way. It's from x squared up to x. And then we just evaluate this integral. Basically from 0 to 1. We get x minus x squared evaluated at y equals x. So it's x squared, x minus x squared. So the value of this is just x, okay, and evaluated at x squared at from x squared to x, so it's gonna give us this, so dy, and then we do a equals so this is gonna be a function of x. I'll tell you why. Let's see. Now it's gonna be xy minus x squared y from 0 1, y equals 1, and y equals 0. So a equals x minus x squared, and this is a function of x. We can find now the area. Why is it a function of x again? Okay, so here I do have a minor issue. Okay, my issue is that I did dx before dy. So now basically I'm gonna do this and then I'm gonna evaluate with respect to x. Okay, so now we get a more precise answer. And it's not with respect to y, it's just x. And this is just the area, just the area bounded by our two curves. So x squared over 2 minus x to the 3 over 3 from 0 to 1. So a equals 1 over 2 minus 1 over 3. which is 3/6 minus 2/6 equals 1/6. That's exactly the area of the region bounded by these two. This 1/6. And that's exactly the area. Now if we want to find the average value of f over r, it's basically we're going to take the double integral of f dA and then divide that by the area of r, and the area of r is just can be obtained either by this method, which is the one we discussed, finding the area over closed region, or if it's a rectangle, you're just gonna multiply the width by the height, or find the area using this method. So it could be average value could equal double integral of r f dA over area of r. Now here we have a rectangle, so we just evaluate the double integral. Yeah. Let's add this and try to solve it. This one is simple. We're gonna just need to evaluate the double integral of f of x cosine xy. Now let's do dx dy. So for dx it's just 0 to pi, and dy is just 0 to 1. And now we evaluate this. So we're gonna get 0, 1. With respect to x is just gonna be integral of x cosine x. Okay, I think this would need some. Okay, so I think simpler we can do is dy dx first and then see what we get. It's gonna make it easier for us to evaluate the integral. Sometimes you're gonna try to make it easier for you to evaluate the integral, and that's what we exactly gonna do here. So gonna be minus x sine of xy, sine of xy minus, okay, so minus x squared sine of xy. Okay, and that's because we treat y as x as constant, so we have it here. Okay, and so we evaluate from 0 to 1. Y equals 0, or y equals 1, y equals 0 of dx. This is just 0 pi minus x squared. Now let's take the minus out. X squared sine of x. Now if we put y equals 0, sine of 0 is just 0. So now we need to evaluate this, and this would need some. This will require integration by parts. So let's do that. Let's integrate by parts. So uv minus integral of v du. So let's test u equals x squared. So du equals 2x. And then v equals sine of x dv equals sine of x dx. And then v equals minus cosine of x. Now we're gonna get minus x squared cosine of x minus the integral of 2x cosine of x dx. Now you will need to integrate again, so u equals 2x, du equals 2 dx, and then dv equals cosine x dx. Okay, so v equals sine of x. Now uv, so we're gonna get 2x sine of x minus the integral of v du, so 2 sine x dx is gonna equal to 2x sine x minus or plus 2 cosine of x. Of course, plus c, but we won't need it here. And so our integral becomes minus so first it was minus x squared cosine of x, and then we add 2x sine of x, and then plus 2 cosine of x, evaluated from x equals 0 to x equals pi. So for x equals pi, we're gonna get so this is the integral. For pi, we're gonna get minus pi squared. No, actually, so cosine of pi is -1. Yep. So minus pi squared plus pi squared plus sine of pi is 0, so 0, and then 2 times pi is just plus 2. Okay, and then minus, if we evaluate at 0, it's gonna be 0, and sine of 0 is 1. No, sorry, cosine of 0 is 1, but x will make it 0, and here also we have 0, and then cosine of 0 is 0, so it's just minus 0. So our answer is pi squared plus 2. Now this is only the definite integral and definite integral. Now if you want to find the average value of f, it's gonna be basically pi squared plus 2 over the area. What is the area here? The area is basically the area of the rectangular region is the rectangular region goes from xy, it goes from 0 up to pi, and then here it goes from 0 up to 1, and so the area is just pi 1, so 1 pi pi, so it's pi times 1, and so it equals pi squared plus 2 over pi. This is the average value. You can find it through a calculator to find exactly how much that is. Let's just check our answer. Okay, so we got a different answer here. Let's see what went wrong. So we first integrated with respect to y, and that gave him okay, so basically what I messed up here is that so here instead of multiplying by x, I should have divided by x. So, and when we divide by x, we just remove that x. So for integration, we divide and not multiply. So basically we got this just simple integral, and it was way simpler than what we did. We did like partial, but if you had a problem with integration by part, you know how to do it now. Just basically minus, okay, so minus sine of x dx, okay, and so sine of 0 is so sine of x, and then sine of 0 is just 0. Now integrate this, gonna be cosine of x from 0 to pi, which is just cosine of pi is 1 minus oh. So cosine of 0 is 1, cosine of pi is -1, so -1 minus 1 to get -2. Here you got a +2. Okay, I had an extra negative sign here. Yeah. No, it's gonna be like this. Minus cosine. And then it's gonna fix this. It's gonna give us +2. And now, from this, we get average value of f is just 2 over, we got the area is pi. And that's exactly how it is. And these are some examples if you want to solve them. I'm not gonna go through them, but you can solve them by yourself. Thank you for watching this video. I hope you